Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Energy and Earth Materials. This is a lab manual in Unit 2. Section 1, Earth's Changing Surface, a scientific record in a volcano myth. Don Swanson is a scientist who studies volcanoes. He is a former director of the scientific observatory that overlooks an active volcano in Hawaii called Kilauea. Volcanoes are structures formed around a hole in Earth's crust that release magma, hot, molten rock. One evening, he was reading a book of Hawaiian chants that told the legend of the goddess Pele. Islanders believe she was the goddess of Kilauea. According to the legend, Pele was violent and jealous. One time, she set fire to a forest because she was angry with her sister. That set off a chain of events that ended with the sister digging furiously in the ground, sending rocks flying in the air. As he read, Swanson realized that the legend was actually providing a description and timeline of the two largest volcanic events that had happened on the island. First, the burning forest was most likely a lava flow from Kilauea in the 15th century that lasted for 60 years. This lava flow was so massive that it covered almost 430 square kilometers of the island of Hawaii, dramatically reshaping the land. Secondly, the rocks flying in the air was likely the result of a collapse of part of the volcano that resulted in a volcanic feature called a caldera. A caldera is a special kind of volcanic crater. The reference to these two events dramatically changed how scientists viewed Kilauea because it offered a different timeline for when these events took place from what scientists had previously believed. Scientists are constantly looking for clues in Earth's surface to figure out what happened in the past. They were excited to discover that the chants hold clues to Earth's changing past and are now digging deeper into the chants for more clues. Volcanoes connect Earth's systems. Scientists study volcanoes to learn more about Earth's interior and some of the natural processes that have shaped the planet over time. For example, the volcano in Hawaii, Kilauea, has been constantly erupting since 1983. As a volcano erupts, it spews lava. It also releases gases and ash into the atmosphere. Scientists are still trying to figure out exactly why the volcano has been so active and where exactly it gets its heat source. The scientific inquiry has real-world consequences. As lava has erupted from the volcano, it has destroyed many homes, as well as the visitor center in the Hawaii Volcanoes National Park. In just one summer, it buried 100 homes, a church, and a store beneath 15 to 24 meters or 50 to 80 feet of lava. Scientists who study volcanoes need to have an understanding of Earth's different systems and how those systems interact together. Remember that a system is a set of connected, interacting parts that form a more complex whole. Earth is so massive and so complex that scientists study smaller systems to better understand how everything works. There are four main systems: the geosphere, atmosphere, hydrosphere, and biosphere. The volcano itself is part of the geosphere. The geosphere is the Earth system made up of Earth's solid materials, including its interior and surface features, such as landforms including mountains, valleys, rocks, and soil. Volcanoes release gases into the atmosphere. The mixture of gases, dust, water vapor, and other molecules above Earth's crust. The hot lava and ash can be deadly for the biosphere, which is the Earth system made up of all living things. Earth's surface changes over time. Scientists know that Earth's surface is constantly changing, and volcanoes are just one natural process that change Earth's surface over time. Scientists study Earth's processes to better understand the scale of the changes. Remember that scale is the size, extent, or importance, magnitude, of something relative to something else. For example, some natural processes occur rapidly. Others occur much more slowly and can take place over millions or even billions of years. These are time scales. At the same time, the changes to Earth's surface can be small, such as when wind or water carry small bits of rocks or other material to another location. Other changes are much more massive, including the uplifting of land to form a mountain range. These are spatial scales. The changes to Earth's surface are caused by interactions among all of Earth's systems. For example, when rain falls to the surface, it involves the interactions of two Earth systems, the hydrosphere and the atmosphere. The hydrosphere is made up of all of the water on Earth, including ice, liquid water, and water vapor. As the addition of energy from the sun causes water molecules on Earth's surface to heat up, they evaporate and turn into water vapor, which is held in the atmosphere. Water is constantly cycling between the hydrosphere and the atmosphere. When water vapor cools and falls back to Earth's surface, it moves over and changes Earth's solid materials, which make up the geosphere. Living things depend on all of the other systems for survival. At the same time, living things impact their surroundings as they breathe air, drink water, and live on Earth's surface. Energy changes Earth's materials. Geologists are scientists who study Earth's structure, as well as the processes that have shaped the planet. The primary focus for geologists is the geosphere and how the other systems interact with it. For example, as Kilauea erupts, it connects all four systems, but it begins with an understanding of the materials that make up Earth and how those materials are changed by heat and pressure. Rocks are some of the most common materials on Earth. Most of the Earth's ocean's floors are made up of a dark, finely grained rock called basalt. Most of the continents are made up of granite, a coarse rock that often looks pink with black specks. Both granite and basalt have something in common. Like all rocks, they are made up of mixtures of minerals that have been pressed together by heat and pressure. A mineral is a naturally occurring, inorganic solid with a crystal structure and its own chemical formula. Minerals are made up of different elements that join together. Both granite and basalt have large amounts of the elements silicon and oxygen. Geologists need to have a good understanding of the relationship between energy and matter and how energy changes matter. This is because none of the changes that take place on Earth's surface can occur without energy. Some of the energy that shapes Earth's surface comes from deep within Earth's interior. Earth is divided into 4 layers. The inner core is Earth's hottest layer and is made up of a mixture of solid iron and nickel. It is surrounded by an outer core that is made up of a less dense mixture of liquid nickel and iron. Surrounding the inner and outer core is the mantle, which is mostly molten, semi-solid rock called magma. The mantle makes up almost 2/3 of the Earth's mass, around 83%, and is about 2,900 kilometers or 1,802 miles thick. Earth's crust is the hard rock layer of the planet that supports the continents and oceans. The crust is Earth's thinnest and coolest layer. The mantle is in constant motion, powered by the transfer of energy between Earth's warmer and cooler materials. Remember that heat is energy that has transferred whenever two substances are at different temperatures, and it always flows from faster moving atoms, a higher temperature, to slower moving atoms, a cooler temperature, until both substances reach the same temperature. Because of Earth's structure, heat is continuously flowing from Earth's center outward. Heat from Earth's core warms the lower parts of the mantle through conduction, heat transfer that occurs when molecules collide. When molecules of the mantle near the core are heated, their particles move faster. As the particles move faster, they become more spread out and less dense than the cooler upper mantle rocks, whose particles are much slower. The cooler particles clump together, becoming denser. The warmer rocks rise while the cooler rocks sink, creating slow currents within the mantle. This motion describes a form of heat transfer called convection. Convection in Earth's mantle plays a major role in shaping Earth's surface. Earth's surface is fragmented into drifting slabs of solid rock called tectonic plates. As magma moves beneath the crust, it pushes the tectonic plates toward or away from each other. The tectonic plates are made up of Earth's outermost 100 kilometers, made up of the crust and coolest, strongest part of the upper mantle. This is called the lithosphere. The lithosphere floats on a zone of weak, melted rock called the asthenosphere. The places where Earth's tectonic plates meet are called fault lines. The plates move extremely slowly, no more than a few centimeters a year, although the different plates move at varying speeds and in different directions. Scientists continue to study the complex behaviors of the plates. Scientists know that as plates come into contact with each other, they transfer tremendous amounts of energy that cause various geological processes to happen at their boundaries. Their movements cause mountains, valleys, and oceans to form. These collisions between the plates are also the cause of earthquakes and volcanoes. Earthquakes are the shaking of the ground caused by a sudden release of energy when two tectonic plates suddenly slip past one another. When magma reaches the surface during an eruption, it is called lava. Because of how they are formed, earthquakes and volcanoes are not found randomly across Earth's surface. Instead, most are found along plate boundaries, on the edges of continents, near island chains, or underneath the ocean. The cycling of Earth's materials. As the tectonic plates move, they change Earth's surface and materials in different ways. For example, all of the rocks that are on Earth today are made of the same matter that existed when dinosaurs roamed. But rocks do not stay the same. The matter is reshaped and reformed over millions of years into new rocks with different properties. Most of the rocks found on Earth today started out as magma deep within Earth's core. Over millions of years, the magma hardened, changed form, wore down, and reformed into new kinds of rock. The processes that form, break down, and reform rock from one category to another are called the rock cycle. Heat and pressure are the primary causes of these changes. As far as 200 kilometers below the Earth's surface, temperatures are hot enough to melt most rocks. It takes temperatures between 600 and 1,300 degrees Celsius, or 1,100 and 2,400 degrees Fahrenheit, to melt rock. When two tectonic plates collide with one another, one plate sometimes is pushed beneath the other plate back into the mantle. Because of the extreme temperatures, much of the rock melts, becoming magma again. At these temperatures, rocks can also become deformed without melting. For example, when tectonic plates collide, they compress the materials making up Earth's crust. The result is that the crust becomes shorter and thicker, building mountain ranges. When two tectonic plates move away from each other, they stretch the crust, causing it to become thinner. Deformation is a very slow process, taking millions of years. When magma cools into a solid, it forms a category of rock called igneous rock. Basalt and granite are both forms of igneous rock. As the magma cools, different sized crystals are formed at different temperatures. This means the atoms are neatly organized to form a repeating pattern. This process is called crystallization, and it can occur rapidly or slowly. Slow cooling produces larger crystals than quick cooling. For example, when lava spews from a volcano, it cools very quickly when it is exposed to the cooler temperature of Earth's ocean or atmosphere. This produces small crystals. In contrast, sunk magma is pushed slowly towards Earth's surface over many years. This magma will cool, but at a much slower rate than magma erupted by a volcano. This produces much larger crystals. Another category of rock is formed as a result of the tremendous heat and pressure of Earth's interior. Metamorphic rocks are rocks formed in chemical reactions where one type of rock is changed by pressure or heat into a new type of rock with different properties. For example, the heat of Earth's magma and the pressure of the rock layers above turns soft limestone into hard marble. the surface, energy from the sun is the primary source of change to rocks. The sun heats Earth through radiation, which is heat transfer that occurs without contact between the heat source and the object heated. Sunlight carries solar energy. When that energy reaches Earth, some of it is reflected back into space. Some of it is absorbed by the molecules of the atmosphere, and the rest of the energy is absorbed by Earth's surface, land and ocean, as thermal energy. However, different parts of the planet are heated differently. The atmosphere absorbs heat differently from the land, and the land absorbs heat differently from either the atmosphere or the ocean. Beyond that, different regions on Earth receive different amounts of solar radiation at different times of the year. We'll explore these concepts in more detail later on in the year, but for now, it's important to understand that Earth is unevenly heated. The result of these temperature differences is that heat is transferred around the planet through conduction and convection. For example, wind is a result of temperature differences in the atmosphere. Wind is caused by convection currents similar to the convection currents in Earth's mantle. As cold air sinks in the atmosphere and warm air rises, it creates wind. Changing temperatures also cause water to change from a solid, ice, to a liquid and gas, water vapor, and back again. For example, as water vapor cools off in the atmosphere and turns back into liquid water, gravity pulls that liquid water back to the surface as precipitation. All water on Earth's surface also moves, pulled downward by the force of gravity. When rocks on Earth's surface are exposed to changes in temperature, wind, water, or biological forces, such as plants or animals, they experience weathering. Weathering is the result of interactions among all of Earth's systems. For example, one of the gases in the atmosphere is carbon dioxide. When water falls to Earth's surface as rain, it carries some of this carbon dioxide, making the water slightly acidic. This slightly acidic water causes chemical weathering of the rocks on Earth's surface. Chemical weathering occurs when chemical reactions break down the bonds holding the rocks together, causing them to fall apart, forming smaller and smaller pieces. This is an interaction between the hydrosphere and the geosphere. The chemical weathering breaks down the rocks, transforming the matter into new substances with different properties, including salt and other minerals. Chemical weathering generally occurs gradually over time. Wind and water are also called mechanical weathering. Mechanical weathering takes place when rocks are torn apart by physical force without any change in their chemical nature. The constant freezing and thawing of water is one of the most common types of mechanical weathering. This is an interaction between the geosphere and the hydrosphere. As rock is weathered, it is broken down into sediment. That sediment is then transported by wind, water, or gravity to new locations, a process called erosion. Excuse me. Sediment formed from weathering and erosion slowly accumulates in layers in oceans, lakes, and valleys through a process called sedimentation. Heat and pressure compact the layers of sand, soil, clay, gravel, and other sediment that built up in one location over time into sedimentary rock. The oldest sediment forms the bottommost layers of the rock, while the new layers form at the top. An eruption lasting more than 30 years. A result of all of these Earth processes is that Earth's surface is constantly changing. Energy from Earth's interior causes changes from within the planet, while energy from the sun powers changes on Earth's surface. And these processes are continuous, which means that Earth's surface will continue to change. Scientists study the processes to better understand the forces that shape the surface and to predict future changes. For example, scientists have set up a station that continuously monitors the eruption at Kilauea. Anyone can follow the changes to the volcano, and millions of tourists have joined scientists in watching the changes take place. Scientists have learned that the ongoing eruption, which began in 1983, has added 500 acres of new land. This happened as the lava cools into igneous rock on the surface. They have also improved their understanding of how volcanoes work in general. From their perch, scientists watch the volcano itself change. For example, a new crater filled with a lake of lava was created in 2008. Scientists are also studying what is happening beneath Earth's surface. They are collecting a variety of different data, including changes in pressure to the magma beneath the volcano. They use that data to better understand the volcano as a system. Because of this, they have been able to improve their monitoring, such as predicting the path that lava will flow, similar to how scientists can predict upcoming floods. Section 2. Finding energy sources on Earth. A geological treasure hunt. Shar Anderson spends her days using computer models and gathering data about the properties of rocks in particular locations. She sees her job as a treasure hunter, looking for clues on Earth's surface and underground. Anderson is a petroleum geologist, and her job is to analyze data to determine where the best locations are to drill for oil and gas. Oil and gas are both fossil fuels, non-renewable energy sources that formed millions of years ago from plant and animal matter. They are non-renewable resources because they take millions of years to form and therefore cannot be replenished in a short time. The search for oil and gas is part of geology because some of the processes that shape Earth's surface, including the movement of tectonic plates and the processes that power the rock cycle, are also responsible for the formation of fossil fuels. Petroleum geologists like Shar Anderson use what they know about the movement of the tectonic plates and the properties of different rocks to gather data using a variety of different tools. They then analyze the data for patterns in Earth's geology that might indicate the presence of fossil fuels. This is important because fossil fuels, like many natural resources, are not distributed evenly around the planet. They are formed through specific natural processes, and those processes help to determine where fossil fuels can be found. Finding fossil fuels begins with an understanding of how interactions between the geosphere and the biosphere caused them to form. Millions of years ago, oceans covered most of Earth. The oceans were home to tiny sea animals and plants called plankton. Like all living things, these plants and animals had chemical potential energy stored in their bodies. When those organisms died, they sank to the bottom of the ocean. Sand and silt covered their remains. Over millions of years, the same pressure and heat that caused the sand and silt to turn into sedimentary rock also caused chemical reactions that broke the organic matter down into more basic structures. Organic refers to anything that is living or was once living, such as fallen leaves or animal remains. Anything that is not living and never was living is inorganic. Water and rocks are both inorganic. The breakdown of the organic matter led to the creation of hydrocarbons, chemical compounds made up of hydrogen and carbon. Crude oil is one kind of fossil fuel that is made of heavy and complex hydrocarbons. It is a liquid that is found in underground reservoirs and remains a liquid when it is brought to the surface. Natural gas is another fossil fuel that is made of light and simple hydrocarbons. It is found wherever there is crude oil, but it can be found on its own as well. Coal is a third fossil fuel that was formed when ferns and other tree-like plants died and became buried by layers of sediment. Once geologists have a good sense of how fossil fuels are formed, they then look for clues in Earth's geology to try to figure out where fossil fuels might be found. It's not easy because fossil fuels rarely stay where they are formed. Because Earth is a dynamic planet, once oil and gas are formed within rocks, they continue to move around the planet in ways both big and small. Let's start with the small movements. Oil and gas form into a type of sedimentary rock called source rock from which hydrocarbons are formed. Source rocks have organic material from the once living organisms as well as inorganic sediment. Over time, pressure from the weight of the layers above forces the crude oil to move from the source rock. It begins to accumulate in a reservoir rock. Reservoir rocks hold oil and gas like a sponge. This is because they tend to have a lower density, the mass of a substance in a given area. They are also permeable and porous. Porosity refers to the number of spaces between particles in a substance. Porous rocks have tiny spaces called pores that allow substances such as oil to collect. Permeability refers to the ease with which substances move through a material. Oil and gas move through the permeable reservoir rock. Some of it will reach Earth's surface and seep out. More often, however, it will reach a kind of impermeable rock called cap rock. The cap rock holds the oil in place. Over many thousands or millions of years, the oil slowly builds up, forming a reservoir. These reservoirs are called oil and gas traps. The tectonic plates can also cause entire reservoirs to move over millions of years. These complex motions make oil and gas reservoirs very difficult to find. The search for fossil fuel. So geologists use a variety of instruments to help them in their search. For example, they look for evidence of source rock, reservoir rock, and cap rock. They also look for deposits of salt because salt indicates there used to be an ocean. Because of how fossil fuels are formed, evidence of an ocean suggests that fossil fuels might be found there. They also analyze surface features, surface rock, and soil types. River deltas, deserts, and Arctic areas hold most of the oil and gas in the world today. Geologists can also use seismic shock waves to find oil and gas reserves. The shock waves travel beneath Earth's surface. When they come into contact with various rock layers, they are reflected back. The reflections travel at different speeds depending on the type or density of rock layers through which they must pass. Geologists use instruments called hydrophones to capture information about the shock waves and then interpret the data to look for signs of oil and gas traps. Once geologists find a possible oil and gas trap, they can mark the location using GPS coordinates on land or with a buoy on water. If it sounds as if a rock might contain oil or natural gas, the companies begin to drill to release the oil and gas from the rocks, which are often far below Earth's surface. Oil sources are often found below the ocean floor, so oil companies have developed technologies that allow them to drill offshore. Refining oil. Finding the oil is just one part of the process. The next step is removing it from the ground and then refining it so it can be used. When crude oil is taken from the ground, it contains hundreds of different types of hydrocarbon chains that are mixed together. There are 4 main ways to change hydrocarbons: organizing molecules by size, breaking down large molecules into smaller ones, combining small molecules to produce larger ones, or changing the shape of the molecules. The length of the chain determines certain properties. As the hydrocarbon molecules get longer, they move from a gas to a liquid. Hydrocarbons with up to 4 carbon atoms are gases. Hydrocarbons that have between 5 and 16 carbon atoms are liquids, and those with more than 16 carbon atoms are solids. This means that the longer and more complex hydrocarbon chains cannot flow freely and so are more difficult to get out of the ground. By adding heat, refineries are able to separate the various components of crude oil. Longer hydrocarbon chains have higher boiling points than shorter chains. For example, the asphalt that makes up pavement comes from extremely long hydrocarbon chains that have up to 150 carbon atoms. Asphalts are highly viscous with a boiling point of 525 degrees Celsius or 977 degrees Fahrenheit. In contrast, methane, the primary component of natural gas, is the simplest hydrocarbon. It is made of a single carbon atom surrounded by 4 hydrogen atoms. Methane is colorless, odorless, and has a boiling point of negative 164 degrees Celsius or negative 236 degrees Fahrenheit. How fossil fuels are used. Fossil fuels play an important role in our society. They are a primary source of energy and are used to power many vehicles, electronics, and many other modern conveniences. The reason that fossil fuels are an energy source goes back to the chemical potential energy that the organic matter holds within it. When fossil fuels are burned, that stored energy is released in an exothermic reaction. Exothermic reactions give off energy, making the surrounding temperature warmer. Exothermic chemical reactions that burn fossil fuels are some of the primary sources of energy in the United States today. Refineries take the crude oil and turn it into gasoline and many other useful petroleum products. Petroleum refers to both crude oil and the products extracted from it at petroleum refineries. Petroleum is used in a wide range of consumer goods, such as detergent, fertilizer, synthetic fibers, vitamins, plastic, CDs and DVDs, candle wax, and Band-Aids. Synthetic materials are those materials formed through a chemical process developed by humans, as opposed to those of natural origin. Section 3, a renewable resource. Renewable versus non-renewable. The United States uses 18 million barrels of crude oil a day. Without it, many things that we take for granted wouldn't be able to occur. For example, factory machines would stop working. Cars and airplanes wouldn't be able to move. Many common goods, including plastics and fertilizers, wouldn't exist. But oil, natural gas, and coal are all non-renewable resources because they take millions of years to form and therefore cannot be replenished in a short time. Fossil fuels pose another challenge. Burning them produces pollutants that are released into the atmosphere. One such pollutant is carbon dioxide, a gas that traps heat in Earth's atmosphere. This is called the greenhouse effect. The greenhouse effect is essential for life on Earth, but it relies on a balanced amount of carbon in the atmosphere. Carbon dioxide released from fossil fuels upsets the natural balance. Fossil fuels currently supply about 80% of the world's energy. So scientists and engineers are trying to find energy sources that are renewable, can be replenished in a short period of time, and are less polluting. Examples of renewable energy include solar energy, wind, geothermal energy from Earth's internal heat, hydropower from water, and biomass, organic material made from plants and animals. Using biomass for energy. Scientists have known for many years that biomass can be used for energy. People first discovered that wood from trees could be burned to produce thermal energy hundreds of thousands of years ago. Like fossil fuels, biomass contains potential chemical energy because it was once living. When biomass such as firewood is burned, that energy is transformed to thermal energy that can be used to do work. For example, people have been using fire as an energy source for 1 million years. When a pot of food is put over a fire, such as in the image on the right, the thermal energy is transferred to the pot and then the food outside the pot through conduction. This transfer of energy causes the pot and the food to warm up. However, burning wood in a fire isn't very efficient. A lot of the energy is transferred to the atmosphere. Look at the picture again and imagine that you're sitting next to the fire. The air near the fire is also warmed by the fire. Because of the conservation of energy, the heat that is warming the air is not warming the pot or the food. When some energy is transferred out of the system and into the air, it means there is less energy available to do work, in this case, warming the pot and the food. Producing ethanol. In the last 100 years or so, scientists discovered that many plants have sugars that can be converted to usable energy. Ethanol is a renewable fuel that is made from the sugars found in plant matter, such as corn and sugarcane. Wheat, barley, and potatoes can also be used to make ethanol. Ethanol is made by fermentation, a chemical reaction in animal or plant matter brought about by microscopic yeasts, bacteria, or molds. Fermentation results in the breakdown of complex organic substances into simpler substances. Fermentation is a common process. If you have ever eaten bread, cheese, chocolate, or yogurt, you have had fermented food. Yeast are microscopic organisms that get energy by eating simple sugars, such as glucose, that are found in most plants. The yeast chemically break down the sugar into substances that it can use. When yeast and sugar combine, a chemical reaction occurs that produces ethanol and carbon dioxide. Ethyl alcohol can be blended with gasoline or used by itself as a fuel. Since 1978, Americans have driven more than 2 trillion miles, 80,000 trips around the world, on ethanol blended gasoline. When combined with gasoline, ethanol helps the fuel burn more cleanly. Some estimates say ethanol produces 25% fewer greenhouse gas emissions than fossil fuels. Benefits and drawbacks of ethanol. But there is some controversy over the widespread use of ethanol. The United States currently produces about 2 million gallons of ethanol each year, 2 billion gallons, primarily from corn. Critics worry that the focus on fuel reduces the amount of land that is available to grow corn for food. It also requires a lot of energy to grow corn. In addition, farmers rely on fertilizers, which are often made from fossil fuels. If people do not replant corn or other biomass sources as fast as they use them, biomass energy becomes a non-renewable energy source. There is also debate over the amount of energy needed to actually produce the ethanol. A gallon of pure ethanol contains 34% less energy than a gallon of gasoline. Some studies suggest that it takes more energy to produce ethanol than the amount of energy that ethanol provides. Other studies show the opposite, so the research is ongoing. Scientists are exploring alternative sources of biomass, looking at plant materials that is not a food source. Cellulosic ethanol is a promising area of research, although much more still needs to be learned. Cellulosic ethanol comes from sources that are not used for food, such as corn stalks, switchgrass, and wood chips. Plant cell walls are made of cellulose, which is a type of sugar molecule. Cellulosic ethanol is more complicated and therefore more expensive to make than it is to make ethanol from corn. Wow, I learned a lot reading Energy and Earth Materials. I hope that you did too. I'll see you tomorrow with another one. Bye.